We're going to explore areas of polygons in this lesson, and we'll start with something very straightforward, which is a rectangle. So imagine we have a rectangle that has a one dimension of 6 units and one dimension of 4 units. Now, I intentionally didn't use the words length and width because in math, length and width are somewhat arbitrary. Any dimension can be the length, any other dimension can be the width. You don't want to get hung up on the idea that length is the longer of the two, and width can also be a little bit confusing for some people. So, a rectangle has 2 dimensions, and in this case, let's make it 6 and 4. So, most people remember the area formula for a rectangle is just simply length times width. It's just a product of the 2 dimensions, and you can justify this very easily graphically. You can break this 6 unit dimension into 6 sort of unit wide strips, and the 4 you can break that up quite easily as well, and then it's just a matter of counting up all the squares, and you can see very easily it's 6 times 4, so you get 24. So the area here is simply 6 times 4, 24. Now let's take a look at triangles. So if we have a triangle that is a right triangle, so let's imagine a right triangle, we can kind of complete this right triangle, if you like, and make a rectangle. And the rectangle is going to have one dimension equivalent to one of the legs of the right triangle, and the other dimension will be the other leg of the right triangle. So you can see by symmetry that these 2 right triangles are identical, they're congruent. Each of the sides of the triangle is the same, the hypotenuse is shared. One of the legs, the opposite pair, is equal, and the other leg, the opposite pair, is equal, and all the angles are the same as well. So it's pretty obvious that the area of the triangle is simply the area of the rectangle divided by 2, and the area, let's imagine the width here, well, we'll use the same dimensions, 6 and 4. So again, this area would simply be 6 times 4 divided by 2, which in this case would be 12. And sometimes the formula for a triangle is given as base times height divided by 2. One of the things we're going to see very shortly is that the base of a triangle, again, it's just any side of the triangle. It doesn't have to be the side on the bottom. In English, we normally think of base being bottom, but it doesn't have to be the side on the bottom. The orientation doesn't really matter. Now, easy enough to justify a triangle area as simply half of a rectangular area when the triangle's a right triangle. But what if the triangle's not a right triangle? So what if we have a triangle like this, where it's clearly not a right triangle? Well, you can actually make a rectangle that surrounds or bounds the triangle by just putting in a couple of vertical lines and a horizontal line. And so now we've got a sort of a bounding rectangle, and if we add one other little dotted line here, you can see that you've actually broken this triangle into 2 right triangles, and each of the right triangles, as we've seen in the previous example, can be thought of as half of a rectangle. And so by the same token, the entire triangle here is just half of the bounding rectangle. Now, in this case, we refer to that third dotted line that we added as the altitude. You can call it the height of the triangle if you like. The altitude is the a more formal word, and you'll see that word crop up. And then this is the base of the triangle. So we have the base times the altitude, or base times the height, divided by 2 once again for the area of this triangle. So what I was saying earlier is that the altitude and the base, you don't have to think of the base as the bottom. So we can have a triangle, for instance, oriented like this, where the base might be this side over here. Now, if that's the base, then the altitude, or height if you like, is a line segment that is perpendicular to the base, passing through the vertex opposite the base. So that would be our altitude for this particular triangle if we choose to make the side indicated the base. Now, there is another type of triangle where the altitude is actually outside the triangle, and that's an obtuse triangle. So an obtuse triangle is a triangle containing an obtuse angle, one bigger than 90 degrees. And the altitude, again, has to be perpendicular to the base. So if I make this side the base, then the altitude's got to be perpendicular to that, but it has to pass through the vertex opposite the base, which means that this is our altitude right here. And if you extend the base, you can see that it forms kind of a right triangle there. And the altitude and the base are always perpendicular to one another. So when you're calculating the areas of these triangles, you need to know what this altitude or height is. And sometimes that's given, sometimes you have to calculate it. Let's take a look at a special triangle, an equilateral triangle, and see if there's a way we can find the area of the equilateral triangle. So an equilateral triangle, if you recall, has all three sides equal. And let's start off with one that has sides of length 2. Now, we can draw an altitude, and because of the symmetry of the equilateral triangle, the altitude splits the triangle in half. That is not always the case. You can see in the one above it, it certainly doesn't split the triangle in half there. But this time, because of the symmetry, it splits it in half, which means that each of these pieces has a length of 1. And we saw that the ratio of sides in a 30, 60, 90 triangle, which is half of that equilateral triangle, was 1 root 3, 2. We could have figured that out also using Pythagoras, if you like. So we've got everything we need to find the area of this triangle. The area is going to be the base, which is 2, regardless of which side you pick, it's going to be 2, times the height or altitude, which is root 3, divided by 2. The 2's cancel out, and you get an area of root 3. Now, can we do this sort of more generally for any kind of equilateral triangle? Certainly. The formula works out the following way. If we make the side length s, all three sides are side length s, and therefore this part would be s over 2, and this part would be s over 2, and the altitude would be root 3 times the s over 2. So we get s root 3 over 2, and the area is going to be half of the base, which is s over 2, times the height, which is s root 3 over 2. And the s times s becomes s squared, and then we have s squared root 3 over 2, over 4. And you can see that fits in nicely with the example we started this off with. If s is equal to 2, 2 squared becomes 4. The 4's cancel out, and you get an area of root 3. That's a nice formula to remember, but you're really only going to need that on, at most one question. And if you don't remember it, you can still work it out sort of on the fly. It just might take you a little bit longer. So let's take a look at some other types of polygons, some quadrilaterals. If we have a parallelogram, parallelogram has two pairs of parallel sides, and I'll use the notation for parallel. So single arrow for this pair and a double arrow for the pair on the top and the bottom. So that's a parallelogram. We need to know the height of this, and the height again has to be perpendicular to the bases. So we could make the left and right sides the base, or we could make the top and bottom the base, in which case this is our height. We could also call it an altitude, but for some reason Altitude is usually reserved for triangles. So we have a height there. Now, you can see that by, again, making a sort of bounding rectangle, you end up with a triangle on the left and a triangle on the right. And they're right triangles, and they're identical. So this yellow triangle over here on the left is exactly the same as this yellow triangle over here on the right. And you could imagine actually reorienting the figure and turning this. If you cut it up along the dotted line that I've done the height, you could simply take the piece on the left and shift it over and make a rectangle. And so the formula for the area here is simply the base times the height. So base times height is the formula for the area of a parallelogram. Now there's a special parallelogram we saw called a rhombus. A rhombus, the important characteristic of a rhombus is that all four sides are equal, and there's no other way to make a rhombus except having it be a parallelogram, but the important part of it is that all four sides are equal. Now, if all four sides are equal, and you have a rhombus, then the other important property that comes out of it is that the diagonals bisect one another and form a right angle. That's not always going to be true. That right angle is not always going to be present when you look at the diagonals of a quadrilateral. But in this case, it is true. So let's say you have a problem where you're told the length of the diagonals. So let's say the diagonals are 6 and 8. Can you use that to find information about the rhombus? For instance, the area or even the perimeter. Well, knowing that the diagonals bisect one another means that the shorter of the two diagonals is 3 and 3, and the longer of the two diagonals is 4 and 4. And because these are right triangles, we can use everything we know about right triangles. So you can think of the rhombus as just simply 4 congruent right triangles. And we can figure out the length of the sides, for instance, if we wanted to find the perimeter, using Pythagoras or recognizing it as a Pythagorean triple, a 3, 4, 5 Pythagorean triple. And so the perimeter here is 4 times 5, which is 20. But if we want to find the area, we can think of it as simply 4 times the area of this right triangle. And a right triangle with a leg of 3 and another leg of 4 is going to have an area of 3 times 4 divided by 2, which is 12 divided by 2, or 6. And so the total area of this rhombus is going to be 4 times the area of each of those triangles, which is 6, and so you're going to get 24. Now, you can come up with a formula for the area of a rhombus. The area of the rhombus is just simply the product of the two diagonals, so diagonal 1 times diagonal 2 all over 2. And we can manipulate the diagram of the rhombus to see why that's true. If you think about the product of the diagonals, that would be a rectangle, and I'm going to use red here. If I just extend draw parallel lines to the diagonals, I can actually create a bounding rectangle. So in this case, that bounding rectangle is going to have one dimension the same length as the longer rectangle, diagonal 8, and one dimension the same length as the shorter diagonal 6. And so the total area of that is going to be the product of the two diagonals, 8 times 6. And you can see that in each of the 4 quadrants of that rectangle, the rhombus occupies half of it, and so the area of the rhombus is just half of the area of that total rectangle. Now let's finally take a look at another quadrilateral called a trapezoid. A trapezoid has one pair of parallel sides, so those are referred to as the two bases. And we can make the two bases the top and bottom. Again, they don't have to be. So we've got base 1 and base 2. Now, to find the area of a trapezoid, we could break this into 3 separate figures. And you can see that you get a right triangle on the left, a right triangle on the right, and a rectangle in the middle. And you can do some work with the numbers and usually figure out the area this way. But there's a little faster way, and I'm not going to go into too much detail as to the derivation of this formula. But the area of the whole trapezoid is simply the average of the two bases times the height. So it's base 1 plus base 2 divided by 2, that's the average of the bases, and then multiply that by the height. So let's say we have a base 2 of 4 and a base 1 of 10 and a height of 3. For this particular trapezoid, we'd have an area of 10 plus 4 all over 2. That's the average of 10 and 4, which is 14 over 2, or 7. And we'd multiply that by the height, 3. So we'd get 7 times 3, which is 21. So this trapezoid would have an area of 21.